Item B, intrinsic geometry, exterior algebra in 3D or 2D as it is in this case over here. So B part 2, manifold, push forward and pull back. B part 2, lecture 11, transformation to a second order tensor field. You see, now first set up second order tensor field. You will set up second order tensor field. This tensor field will be in Cartesian coordinates. You see, let the second order tensor be a tensor field. That is a linear map taking two vectors. The definition of tensor we emphasized in previous videos, which I showed clearly. That's why it's a bilinear mapping, taking two vectors. These vectors, it's written in the basis partial r, partial x, partial xi, which this here belongs to r2 xy. You see, the Cartesian coordinates. Now I can express the second order tensor, which is invariant. Now these are the contravariant components, partial xi, partial xi, are the covariant basis. Attention now, I and j is free. In this case here, this is free. With this is dummy now. You see, dummy index is a lower upper index, which is covariant. Now I can expand txx, you see, that's a basis, okay, in Cartesian coordinates, okay. This, our goal is to express this invariant tensor in the polar basis. This is here, belongs to R2, R theta, you see. Now, so you want to write the second order tensor, which is invariant, in terms of r and theta, which belongs to R2, R theta, which is the polar coordinates. You see, I want these components over here, you see. Now, basis vector transformation, just to recall, partial x, cosine theta, partial r, sine minus sine theta over r, you see. Likewise, partial respect to y. This we did in previous videos. We will now substitute this into each term of this invariant tensor here to get the components in the polar coordinate basis. You see, let's denote partial xi, you see, is just this expansion here. See, look at here, I is free index, is a covariant. I over here on the right, on the left hand side is also covariant because I is in the denominator. So these are the bases, okay? So I can substitute here Tij, okay? This is attention now, don't forget that this tensor product. See, just to remind you, you see this notation over here. So I can group this. Now, attention now, ni, r, that's right here. Ni, r, now dummy. Ij is covariant indices, okay? Now, this is these components are contravariant. Don't forget to review you see, vector space and dual vector space, you see. Now, thus, the transformed components in the polar base are, you see, the same notation here, but here, me and you and ni are free. Attention now, this me and ni are contravariant index. Ij is covariant. Now, this is a polar to Cartesian. See, polar to Cartesian. This is Cartesian, this is polar. Now, but here we want the inverse expressed in Cartesian basis in terms of polar basis. So I just write, okay, this is a covariant components in the Cartesian coordinates, okay. Then I can express in terms of this case, okay, these components in the polar coordinates. This is just, don't forget that, this is a chain rule. Chain rule. See? So, these components, okay, of the second order tensor in polar coordinates is just equal to this equality here. This. So, then I can obtain, you see, I mean, look, me and you are free, in this case, free indices in the polar coordinates. Now, me, nu is equal 1, 1, this is TRR, you see, contravariant components. I just substitute over here RR, okay, and then I can write the right hand side over here. Attention now, this is the right hand side belongs to the Cartesian coordinates. The left hand side belongs to the polar coordinates. That's what I want. So I can get TRR, T theta R, TR theta, and T theta theta. You see? Just easy to substitute over here. So let's compute the transformation now. Remember the x's are cosine theta, partial x, partial r is cosine theta, partial x, partial theta is minus r sine theta. As you must recall, okay? Likewise, the Cartesian coordinate y is r sine theta, partial r is just, in this case, sine theta, and partial y, partial theta is r cosine theta. Now we are ready, okay, to obtain the components of a second order tensor, okay, expressed in polar coordinates. You see? That's just substitute from here to here, just easy to see it. Don't forget, I and j are dummy index, okay? We have to apply dummy index on this right hand side of the Cartesian coordinates. You see, it's just here, it's quite easy, you just follow, okay? Now, if you assume symmetric, okay, then in this case, Txi is equal to Ix. So this is a particular case. Now, this is a numerical example. Say, transform a specific tensor, let Txx equal 2, Txy is equal 1, Txyy is equal 3. And use x, you see, I must know the right hand side, the data on the right hand side, just to calculate the left hand side, which are the components of the second order tensor in terms of polar coordinates. You just substitute over here, you see. Then TRR is 3.6, T theta theta is equal 4, you see. just easy. So you substitute this number over here. Attention now. This over here, you see, this expanded. See, using ij as dummy index, just easy. And then you substitute and do the calculation over here. You see, you can get these components over here. Now, observation. We could extend this to transform covariant components like this. Suppose I have Tij over here. Attention now. This will be, in this case, partial I tensor partial j. Attention now. Here I and j, this belongs to the dual. See, ij here in the denominator, so this is upper indices. These are the covariant component. This belongs to the dual space. So we can do the same analysis just to obtain the relation between covariant component which belongs to the dual. Okay? That's it.